Good day, ma'am. Today we're going to discuss the coordinate system and the positioning method. In geodetic surveying, having a reference coordinate system is absolutely essential because it provides the mathematical and physical framework within which all measurements of position, distance, direction, and elevation are made. A coordinate system is a mathematical framework used to define the position of points on the Earth's surface using a set of numbers called coordinates. In geodesy, a coordinate system provides the basis for expressing location, direction, and distance in a consistent way, allowing surveyors, cartographers, and engineers to describe the Earth's geometry and accurately. So we have the common types for the coordinate system. We have the geographic coordinate system, or GCS. It is a system that uses angular measurements to define locations on the Earth's surface. Next is we have the projected coordinate system, or PCS, a 2D representation of the Earth's curved surface obtained by projecting it onto a flat map plane using a mathematical formula called map projections. And lastly, we have the Cartesian or geocentric or Earth-centered coordinate system. It is a 3D coordinate system with the origin of the Earth center of the mass. Next, we have the reference frame. A reference frame ties the mathematical definition of a coordinate system like latitude, longitude, and height to actual observed positions on the Earth's surface through a network of accurately measured points and satellite data. It ensured that all geographic and surveying measurements are consistent, stable, and traceable to a global or regional standard. We have the common reference frame used in geodetic surveying, which is WGS 84 or the World Geodetic System 1984. The standard coordinate reference frame used by the Global Positioning System or GPS ensured all GPS receivers and maps used in common Earth-centered frame. It is used in global navigation, mapping, remote sensing, and geodesy. Next, common reference frame used in geodetic surveying, which is the Philippine Reference System of 1992 or PRS 92. It provides a consistent reference for surveying, mapping, and GIS activities in the Philippines. Next is, what is the difference between geoid and ellipsoid as the models of the Earth's surface? The geoid, it represents the true physical shape of the Earth in terms of gravity, not geometry. The geoid is the equipotential surface of the Earth gravity field that corresponds most closely to mean sea level or MSL and its continuation under the continents. Next, what is ellipsoid? The ellipsoid or spheroid is a mathematically defined, smooth, and regular surface obtained by rotating an ellipse about its minor axis. It serves as a geometric reference surface for latitude, longitude, and the height calculation. And it is more practical to use the ellipsoid in geodetic computations because the ellipsoid provides a mathematically simple and sufficiently accurate model of the Earth shapes.
So the next is the relationship of geoid, ellipsoid, and topographic surface. The first is geoid. It's an imaginary surface that represents the Earth's gravitational potential and approximates the sea level. It's like a slightly squashed sphere that shows how gravity works across the Earth. An difference in height between the geoid and the other surface, like an ellipsoid, helps measure height above sea level. The second is ellipsoid. Ellipsoid is a mathematical shape used to model the Earth's surface, like a perfect but slightly flattened sphere. It's based on specific points, and height measured above the shape are called ellipsoidal heights. The next, topographic surface. Topographic surface is the actual physical surface of the Earth, including land, water, and mountains. When measuring height relative to the geoid, it's called orthometric height, showing true elevation above sea level. Height measurements can be made relative to either the ellipsoid or the geoid. If we measure relative to the geoid, we're getting a height that's closely related to the actual sea level and physical surface. If we measure naman to the ellipsoid, it's a more mathematical measurement used mainly in GPS, concept of coordinate transformation. Coordinate transformation. This concept involves converting coordinates from one system, like a datum or map projection, to another. This is important because different regions or systems might use different reference points or coordinate systems. Accurate transformation ensures that data is consistent and maps align correctly. So, the good example of this is the transformation of WGS84, which is the coordinate system used by GPS, to PRS92 used in the Philippines. This ensures that data from different sources are compatible and consistent. But what happens is two surveyors are using different coordinate systems. The problem is a mismatch of reference frameworks. So, if two surveys use different coordinate system, it can cause errors in measurements, making surveys, maps, and navigation inaccurate. So the solution is this. Actually, there's three solutions of this coordinate transformation. The second is using the same reference framework, and the third is modern tools like GPS.
Point positioning, relative positioning, and kinematic positioning in GNSS surveying. Point positioning. In this method, only one GNSS receiver is used to determine its position independently by receiving signals and navigation data directly from satellites. In short, point positioning is convenient but less accurate compared to other GNSS methods like relative or kinematic positioning. For relative positioning, in this method, two or more receivers are used. One is placed at a known location called the base station, while the other is at a known point called the rover. Both receivers observe the satellite at the same time to compare their data. Overall, relative positioning is very reliable for precise surveying, but it requires careful setup and coordination to achieve accurate results. Kinematic positioning. So, kinematic positioning, this method uses moving GNSS receivers like those on vehicles or UAVs to collect data while in motion. A common type is network RTK, which uses several reference stations to provide real-time correction. In short, kinematic positioning is perfect for rapid, accurate mapping on the move, but it requires good setup and clear signal condition. Why does relative positioning produce higher accuracy? In this method, both the base and rover receivers observe the same satellite at almost the same time. Since they are close to each other, many errors like satellite orbit, clock errors, and atmospheric delays cancel out when their data are compared. So in short, relative positioning gives higher accuracy because it minimizes shared errors between receivers, leaving only a small residual error. So this is the geographic coordinate system. So what is geographic coordinate system? This system locates a point on or near the Earth using angular measurements. These are latitude, which measures how far north, south, or point requires an equator, and longitude, which measures how far east, west is from the prime meridian. Sometimes height is also included to show elevation from the surface. The Cartesian coordinate system. This system uses x, y, z axis with the origin at the Earth's center of mass, also called geocentric. The x-axis passes through the prime meridian and the equator, and the y-axis is perpendicular to x and also lies on the equatorial plane, and the z-axis goes through the North Pole. So, relating coordinate systems positioning methods to real-world surveying and mapping. For mapping and navigation, we usually use geographic coordinates like latitude and longitude because they show global positions directly. However, these coordinates can be converted to Cartesian coordinates for easier mapping and analysis. It's also very important to perform proper coordinate transformation to prevent misalignment of data from different systems. Using the correct datum and map projection ensures that all data line up accurately on maps. That's all. Thank you.
Okay, let's go.